A Quiet History of the Solar System. Chapter 1. Before the Sunday. Imagine a time before the Earth existed, before the oceans gathered, before the moon appeared in the night, before the sun cast its first light across the space that would one day become our home. We are traveling back almost 4.6 billion years into the broad disk of the Milky Way. There is no solar system here yet, no familiar arrangement of planets, no blue Earth moving through a known and measured year. There is only a vast region of gas and dust resting inside a much larger molecular cloud. From a distance, the cloud might seem almost empty. Its matter is spread across an enormous volume, and most of it is invisible to human eyes. Yet it contains nearly everything the future system will need. There is hydrogen, the simplest and most abundant element. There is helium, formed in the earliest age of the universe. And there are smaller amounts of carbon, oxygen, silicon, iron, and many other elements made inside older stars. Those earlier stars lived before the Sunday. Some released their outer layers slowly. Others ended more suddenly. Their material entered interstellar space and mixed with new clouds, carrying the ingredients of rock, water, air, and eventually life. Nothing in the cloud knows what it will become. There is no hidden plan inside the dust. There are only natural laws, immense spans of time, and small differences in density that gravity can patiently deepen. The cloud is cold, only a little warmer than the lowest temperature nature allows. In such conditions, molecules move slowly. Fine grains of dust carry thin coatings of ice. Large regions drift in a darkness that may last for millions of years. But the cloud is not perfectly still. No cloud in the galaxy is completely still. It turns gently within the motion of the Milky Way. Turbulent currents pass through it. Distant stars illuminate its edges. Nearby young stars may send winds and radiation through the surrounding gas. Somewhere within this cloud, one region becomes slightly denser than the space around it. Perhaps the change begins through the cloud's own internal motion. Perhaps material gathers where currents meet. Perhaps an external disturbance, such as the influence of nearby massive stars or the passing wave from a stellar explosion, helps compress the gas. Scientists cannot recover that first moment with certainty. The oldest meteorites preserve clues about the environment in which the sun formed, but not a complete recording of the event. And that uncertainty is part of the story. We know that the cloud contracted. We know that a young star formed within it. We know that the planets were assembled from the disk surrounding that star. But the smallest beginning, the first quiet imbalance, remains partly hidden. Slowly, gravity begins to draw the denser region inward. Atoms and molecules that once traveled on separate paths now move toward a shared center. More material joins them, The central region grows heavier, and its gravity becomes stronger. The process feeds itself. A little more matter creates a little more gravity. A little more gravity gathers a little more matter. Nothing happens quickly on a human scale. Thousands of years pass, then tens of thousands, then hundreds of thousands. The broad cloud becomes a contracting core. Its faint initial rotation becomes more noticeable as it shrinks. Imagine a wide current of water turning almost too slowly to see. As the current narrows, its rotation becomes clearer. In much the same way, the collapsing cloud begins to turn more rapidly as its material moves inward. A new center is forming in the dark. The ancient gas, the dust of earlier stars, and the frozen grains carried through the galaxy are beginning to share one history. For now, there is no sunlight. Only gravity gathering the cloud, layer after layer, through a darkness that is deep but no longer empty. At the center, pressure is rising. Temperature is rising. A small region has begun its long transformation into the Sunday. And around it, almost all the material that will become planets is still in motion, still unformed, still waiting within the turning cloud. Chapter 2. The Hidden Young Sunday. As the cloud continues to contract, its rotation becomes more important. Material falling toward the center cannot move directly inward all at once. It carries motion from the original cloud, and that motion must be preserved and redistributed. The result is a wide, rotating disk. The cloud gradually changes from a roughly rounded shape into something flatter. Gas and dust continue to fall inward from above and below, joining a broad plain around the center. This is the solar nebula, the young disk from which the sun and planets will emerge. It is not a perfectly smooth disk. There are currents, waves, warm inner regions, cooler outer regions, and places where material gathers more densely than elsewhere. At the center, most of the mass is collecting into a young protostar. Gravity draws matter downward into this central body. As the material falls and is compressed, gravitational energy becomes heat. The interior grows warmer, not because the sun is already shining as it does today, but because an enormous weight of gas is pressing inward. The young sun is hidden. A thick envelope of dust surrounds it, absorbing visible light and releasing energy at longer wavelengths. From far away, a forming star like this may appear not as a clear point of light, but as warmth concealed inside a dark cloud. The protostar gathers material from its disk. Some of that material spirals inward. Some is redirected by magnetic fields, winds, and narrow outflows. The exact details are complex, and even now astronomers continue to study how young stars exchange matter and motion with their surroundings. Yet the larger pattern is clear. The center becomes denser. The center becomes hotter. The young sun grows. Around it, the disk extends far into the cold, carrying only a small fraction of the system's total mass. But almost all of its future planets, moons, asteroids, and comets. For a long time, the protostar is not yet a star in the full sense. Its core is warm and compressed, but not warm enough for the steady fusion of hydrogen that will later support it. It continues to contract. The temperature in its deepest interior rises to millions of degrees. Particles move rapidly in the growing heat. Eventually, conditions become sufficient for hydrogen nuclei to begin joining and releasing energy. The change does not resemble a switch being thrown in a single visible instant. The young sun settles gradually into a new balance. Gravity continues to press inward. Energy from fusion pushes outward. Between them, the star finds a long-lasting state. The sun enters the calm central phase of its life, the phase it still occupies today. The light of the young star begins to shape the disk around it. Radiation warms the inner regions. Stellar winds help remove remaining gas. The disk is changing, even while new bodies are beginning to grow inside it. This is an important consequence of the sun's birth. The planets do not form after the star is completely finished. They form during the star's youth, inside a disk that is itself evolving, cooling, thinning, and moving. Every future world is influenced by where it begins, when it begins, how quickly it grows, and what material happens to pass nearby. There is no single quiet assembly line. There are countless local histories unfolding at once. Still from a distance, the whole disk turns with remarkable unity. Nearly everything circles in the same direction. Most of the future orbits lie close to the same plane. This shared motion will remain as one of the clearest memories of the cloud from which the system formed. At the center, the sun is no longer only a hidden ember. It has become a young star. Around it, the disk glows softly in heat and reflected light. Within that disk, grains smaller than sand are beginning to meet. The building of planets has begun. Chapter 3. The quiet work of dust and ice. Close to the young sun, the disk is warm. Farther away, it is cooler. This simple difference in temperature helps shape the architecture of the entire system. In the innermost regions, many volatile substances cannot remain frozen. Water, carbon dioxide, methane, and other compounds tend to exist as vapor. The solid material available there is made mostly of substances that can endure greater heat. Metals, silicates, and other minerals that will later become rock. Farther from the sun, temperatures fall. At different distances, different substances can condense or freeze. There is not one permanent boundary for every kind of ice. There are several condensation fronts, and their positions shift as the disk changes. The best known is the water-snow line, beyond which water can join solid grains as ice. This quiet transition has large consequences. Beyond the snow line, each growing body has access not only to rock and metal, but also to abundant frozen material. More solid matter can be gathered in the same region. Young planetary cores may therefore grow more quickly and become more massive. Inside the warmer region, the supply of solid material is smaller. The worlds that form there remain mostly rocky. At first, however, there are no worlds at all. Only grains. Fine particles move through gas, sometimes drifting together, sometimes passing apart. Electrostatic forces and delicate surface structures can help the smallest grains cling to one another. A grain becomes an aggregate. An aggregate becomes a pebble. Pebbles gather into larger concentrations. Some meetings add material. Some break fragile structures apart. Some objects drift inward and are lost. Others enter regions where they can continue growing. The path from dust to bodies many kilometers wide is still one of the most actively studied parts of planet formation. Astronomers understand many pieces of the process, but the full journey is not simple. One possibility is that large numbers of pebbles become concentrated by motion within the gas. Their combined gravity then allows them to collapse into planetesimals, solid bodies large enough to survive many smaller disturbances. Once planetesimals exist, gravity begins to change the pace. Larger bodies attract more material. They grow into planetary embryos. Their paths cross. Their gravity alters the motion of nearby objects. The disk becomes a place of continuous rearrangement. In the warm inner system, embryos made mainly of rock and metal will eventually become Mercury, Venus, Earth, and Mars. They do not grow in complete isolation. They exchange material with neighboring regions. Some water-bearing objects travel inward from colder parts of the system. Some fragments are scattered outward. The final composition of each planet is the result of many sources and many encounters. Beyond the snow line, growth follows another route. Icy and rocky cores become large enough to attract the hydrogen and helium still present in the disk. Timing matters. The gas will not remain forever. A giant planet must gather much of its atmosphere before radiation and winds disperse the surrounding nebula. Jupiter and Saturn acquire deep envelopes of hydrogen and helium. Farther out, Uranus and Neptune grow with larger proportions of substances that astronomers group under the name ices, including water, ammonia, and methane compounds, even though much of this material is held in hot, compressed forms deep inside the planets. The young system develops two broad families of worlds: small, dense planets near the Sunday, giant planets farther away. But this pattern is not a rigid rule for every planetary system. Around other stars, astronomers have found large planets close to their suns, small planets far away, and arrangements unlike anything in our own neighborhood. Planet formation creates tendencies, not guarantees. Our solar system is one outcome among many possible outcomes. As the planets grow, the disk thins. Radiation from the young sun and nearby stars heats the remaining gas. Winds carry material away. Within several million years, much of the original gas has dispersed. The great building reservoir is closing. The giant planets have acquired most of their gaseous envelopes. The rocky planets are still assembling through a longer sequence of encounters. Countless smaller bodies remain between and beyond them. The system is no longer a smooth disk. It has become a collection of growing worlds, fragments, rings, gaps, and crossing paths. The quiet work of dust has produced something far more complex than dust. Yet the planets are not in their final places. Their gravity and the fading disk continue to guide them. The next part of the story is not only about growth. It is about movement. Chapter 4. A system in motion. Young planets do not always remain where they first formed. As they move through a disk of gas and smaller bodies, they exchange energy and angular momentum with their surroundings. Their orbits can slowly shift inward or outward. Growing planets also pull on one another, sometimes entering temporary resonances and sometimes leaving them. The early solar system was therefore more mobile than the system we see today. Jupiter, the most massive planet, had the strongest influence. Its gravity reshaped nearby regions, scattered smaller bodies, and affected the growth of the rocky planets. Scientists have developed several models to explain how these changes may have unfolded. In one well-known model, called the Grand Tack, Jupiter first migrated inward through the gas disk. Later, after Saturn grew, and the two planets entered a particular gravitational relationship, their migration changed direction, and they moved outward again. This model can help explain why Mars is much less massive than Earth and Venus. The region from which Mars grew may have contained less material than older, simpler models predicted. But the Grand Tack is not a remembered event written in a complete record. It is one possible reconstruction, tested by simulations, and by the patterns left among planets and smaller bodies. Other models can reproduce parts of the same evidence in different ways. The careful language matters. We know the giant planets influenced the structure of the young system. We know their orbits changed. We do not know every stage of their journey. Farther from the Sun, the giant planets may once have occupied a more compact arrangement. As the gas disk disappeared, and as the planets interacted with a broad population of icy planetesimals, their orbits changed again. Some simulations produce a period of instability. The giant planets move into new paths. large numbers of smaller bodies are scattered. Some travel inward. Some are thrown outward. Some leave the solar system entirely. This broad family of ideas is often associated with the Nice model, named for the city where an early version was developed. The timing and details remain under study. The rearrangement may have happened relatively early, while the terrestrial planets were still growing. It may have contributed to the small mass of Mars and to the present structure of the asteroid belt and the distant Kuiper belt. Beyond the planets, some icy bodies are scattered onto extremely wide paths. Passing stars and the gentle tidal influence of the Milky Way can alter those paths over time, helping to form the distant, roughly spherical reservoir known as the Oort cloud. It is so far away that we cannot observe it directly as a complete structure. We infer its presence from the long paths of comets that occasionally return toward the Sunday. Closer to the young Earth, another event is taking shape. The inner planets grow through repeated encounters among planetary embryos. Earth is not born at its present size. It is assembled over tens of millions of years from many bodies carrying different mixtures of rock, metal, and volatile material. Near the end of this growth, the leading model for the Moon's origin describes a meeting between the young Earth and another planetary body, often called Theia. We do not know Theia's exact orbit. We do not know its precise size, angle, or speed. Different simulations explore different possibilities. But evidence from the Earth, the Moon, and their chemical similarities strongly supports a history in which a very large impact played a central role. In space, the event is silent. Two young worlds meet. Their outer layers are heated and transformed. Material from the collision spreads around the Earth in a broad orbiting structure. Over time, much of that material gathers. Fragments interact. Heat escapes. A new body takes shape. The Moon emerges close to the Earth, much closer than it is today. From then on, Earth and Moon evolve together. Tides exchange energy between them. Earth's rotation gradually slows. The Moon slowly moves outward. The length of the day changes across geological time. The Moon does not exist to guard the Earth, and the collision was not arranged for a future purpose. Yet its presence has real consequences. It shapes tides, influences Earth's rotational behavior, and becomes part of the environment in which life later evolves. This is one of the quiet lessons of the early solar system. Events do not need to be intended in order to have lasting meaning. A chance history can still create a deep relationship. By the end of the planet-building era, the system has become recognizable. The Sun holds almost all its mass. The planets occupy separated orbits. Smaller bodies remain in belts, clouds, resonances, and scattered populations. The period of greatest rearrangement begins to fade. Not every orbit is permanent. Not every object has found a final home. But the broad architecture has settled into a form that can endure for billions of years. The long middle of the solar system's life is beginning. Chapter 5. The Memory in Ancient Things. No one watched the solar system form. There was no Earth from which to observe the first light of the Sunday. No ocean reflected the young sky. No living memory crossed the distance from that time to ours. And yet the past was not erased completely. It remains in motion in chemistry, in ancient stones, and in young systems forming around other stars. The first clues came from the sky itself. For centuries, observers measured the paths of the planets. They learned that the planets move around the sun, that their orbits lie close to a shared plane, and that they travel mostly in the same direction. These patterns suggested a common origin. In the 18th century, thinkers including Immanuel Kant and Pierre Simon Laplace proposed that the sun and planets formed from a rotating cloud. Their ideas were incomplete, and some details were wrong, but the central insight endured. A flat planetary system could grow from a rotating nebula. Later, physics gave the idea a firmer foundation. Gravity explained collapse. The conservation of angular momentum explained increasing rotation. Studies of gas, dust, heat, and radiation showed how disks could form around young stars. Then came the stones. Meteorites are fragments of early solar system material that have survived for billions of years. Some contain inclusions formed at the very beginning of the disk solid history. Inside these minerals are isotopes, versions of elements whose nuclei change at known rates. By comparing parent isotopes with the products of their decay, scientists construct radiometric clocks. Different isotope systems provide independent measurements, and together they place the beginning of solid formation in the solar system at about 4.567 billion years ago. This is not the age of every rock or every planet. It is a reference point, the age of some of the oldest known solids formed in the solar nebula. Other meteorites record later stages. Some preserve material that melted and cooled inside small worlds. Some come from parent bodies that were broken apart. Some carry grains that existed before the sun and survived the formation of the solar system. Lunar samples add another record. So do particles returned from asteroids and comets. Each sample answers one question and opens several more. The past is reconstructed not from one perfect clue, but from many imperfect clues that agree in some places and remain uncertain in others. The same is true of distant observations. Modern telescopes reveal disks around young stars. At radio and infrared wavelengths, astronomers can see rings, spirals, gaps, dust concentrations, warm molecules, and flowing gas. Some disks contain clear evidence of forming planets. In others, a gap may have several possible causes. A planet may be responsible, but so may changes in dust, chemistry, magnetic fields, or the structure of the gas. Astronomers therefore compare observations with models. They ask which explanation accounts for the greatest number of details. They revise the models when new evidence arrives. This is not a weakness in the story. It is how the story becomes trustworthy. Science does not need to turn every unknown into certainty. It can hold a clear center while leaving soft edges. The clear center is this: the sun and planets formed together from a rotating cloud of interstellar matter. The cloud collapsed into a star and a disk. Solid material gathered into planetesimals and planets. The young planets moved and interacted. The system changed before reaching its present form. Around that center are open questions. What first caused the collapse? How exactly did the first planetesimals form? How far did Jupiter travel? When did the giant planets become unstable? What was the precise nature of Theia? How much of Earth's water arrived from each source? The answers continue to develop. Somewhere in the galaxy, new stars are forming tonight. Around some of them, disks are cooling. Dust is gathering. Planets may already be carving paths through gas that no human being will ever visit. When we observe those distant systems, we are not seeing exact copies of our own past. We are seeing variation on the same broad physical processes. Each system is another experiment performed by nature. Each one helps us understand what is common and what is unusual. The origin of the solar system is therefore not a single finished tale. It is a quiet conversation between ancient matter, modern instruments, and ideas that become more precise with time. There is comfort in that incompleteness. We do not need to know every motion of every grain to understand where we belong. We are made from matter that passed through older stars, entered a cold cloud, joined a disk, and became part of a planet. The details are still being discovered. The connection is already clear. In Chapter 6, The Long Middle. The solar system today is calmer than it was in its youth. Most of the gas is gone. The planets no longer grow through collisions with neighboring planetary embryos. The largest migrations and rearrangements belong to the distant past. But calm does not mean motionless. Everything continues to move. The sun travels around the Milky Way. The planets travel around the sun. Moons circle planets. Asteroids rotate. Comets fall inward and return to the cold. Gravity connects all of them. Each planet follows an orbit shaped mainly by the sun, but also very slightly by every other body. These influences create cycles, resonances, and slow changes that can unfold over millions of years. One of the clearest examples lies beyond Neptune. Pluto crosses the distance of Neptune's orbit, yet the two worlds are protected from close encounters by a 3-to-2 resonance. During the time Pluto completes 2 circuits of the Sun, Neptune completes 3. Their positions remain coordinated. The paths appear to cross when drawn on a flat page, but the timing and shape of the orbits keep the bodies far apart. Many smaller objects beyond Neptune share related resonances. Moons also enter repeating relationships with one another. These rhythms are not acts of intention. They are stable patterns that arise naturally through gravity. The system is enduring, but it is not a perfect clock whose future can be calculated without limit. On very long timescales, planetary motion is chaotic in the mathematical sense. Tiny differences grow until exact positions become impossible to predict far into the future. This does not mean that the planets are about to leave their paths. It means that long-term stability and perfect predictability are not the same thing. For a human lifetime, the architecture is extraordinarily regular. For the span of civilizations, the planets return again and again according to patterns that can be measured with great precision. For hundreds of millions of years, the broad system is expected to remain recognizable. Small bodies continue to make the system active. Asteroids collide and create families of fragments. Comets lose dust near the Sunday. Occasional impact reshape planetary surfaces. The solar wind flows outward and meets interstellar space. The Sun itself changes slowly. Its magnetic activity rises and falls in cycles. Its light has gradually increased over the age of the solar system. Yet on the scale of an evening, a season, or a human life, it remains a steady presence. This long interval has given Earth time. Time for its crust to change. Time for oceans and atmosphere to interact. Time for continents to gather and separate. Time for life to begin, diversify, disappear in part, and begin again in new forms. The existence of life cannot be explained by orbital stability alone. It depends on chemistry, geology, water, atmosphere energy, chance, and a long sequence of conditions that scientists are still working to understand. But continuity matters. Earth has remained in orbit around a relatively stable star for billions of years. That continuity has provided a setting in which slow processes could accumulate consequences. The same is true of the Moon. It has moved gradually away from Earth while tides have changed. The same is true of the planets. Their orbits breathe and shift slightly while the overall system persists. Nothing is perfectly fixed. Nothing needs to be perfectly fixed. The calm of the solar system is not the calm of a frozen picture. It is the calm of a pattern that continues while every part remains in motion. Tonight, Earth is carrying you through that pattern. The planet turns beneath the sky. The Sun is beyond the horizon, or moving slowly toward it. The moon, whether visible or hidden, continues along its orbit. The outer planets travel through distances too large to sense directly. You do not need to hold all of those motions in your mind. Gravity is already holding them. The system has continued through every night that came before this one. It continues now without needing attention. The old cloud is gone. Its matter has become the sun, the planets, the sea, the ground, the air, and the living body resting here. The story of formation has become the quiet background of the present. For a while, there is nothing more to build, nothing more to arrange. Only the long turning of worlds around a middle-aged star. Chapter 7. A future beyond imagination. The long middle will not last forever. Stars change because the fuel in their cores changes. The sun is no exception. Its future follows from the same physics that allowed it to begin. But this future is unimaginably distant. It does not belong to any coming season. It does not belong to the span of human history. It lies billions of years beyond tonight. Very gradually, the sun becomes brighter as the composition of its core changes. Far in the future, Earth will no longer resemble the world we know. Its climate, oceans, atmosphere, and surface will pass through transformations long before the sun reaches its final stages. The exact sequence depends on complex interactions between solar evolution and planetary climate. The broad direction is clearer than the precise dates. Eventually, in roughly 5 billion years, the sun will exhaust most of the hydrogen available for fusion in its core. The core will contract and heat. Fusion will continue in layers around it. The outer regions of the sun will expand. The star will become a red giant. Its light will be warmer in color, while its total energy output becomes far greater. The inner solar system will be transformed. Mercury and Venus are expected to be engulfed. The fate of Earth depends on the balance between the sun's loss of mass, which tends to widen planetary orbits, and tidal forces, which can draw a planet inward. Many models suggest that Earth may also be engulfed. Some details remain uncertain. Either way, the Earth of that era will already be entirely unlike the living planet of today. There is no need to picture this as a single sudden ending. The red giant phase unfolds across immense spans of time. The sun changes, pulses, loses mass, and releases its outer layers into space. Those layers form an expanding shell of gas, illuminated for a time by the hot core left behind. Astronomers call such a structure a planetary nebula, though it is made from a star and has no direct connection to planets. At the center remains a white dwarf. It will contain much of the former sun's mass compressed into a sphere about the size of Earth. It will no longer produce energy through ordinary fusion. It will shine because it begins extremely hot, then cool slowly across ages longer than human language was made to describe. The surviving outer planets, if they remain bound, will move onto wider orbits as the sun loses mass. Smaller bodies will also be disturbed. Some may approach the white dwarf. Some may collide or be scattered. Some may leave. The future system will not be a frozen monument. It will continue to evolve quietly and gradually under gravity. Material released by the sun will mix with the interstellar medium. Some of it may one day enter other clouds. Perhaps a portion will become part of new stars or planets. There is no guarantee for any individual atom, but the larger galactic cycle continues. Matter gathers. Stars form. Stars change. Matter is released again. Our solar system belongs to that cycle. It began with material from older generations of stars, and it will eventually return material to the galaxy. This does not make the present smaller. It makes the present part of something larger. The ending of the sun is not approaching us tonight. It is not waiting just beyond the darkness. It is a prediction carried across billions of years, useful because the laws of physics allow stars to be understood across time. Tonight the sun is stable. It has hydrogen in its core. It has billions of years remaining in its main sequence life. Earth continues to circle it at the distance where our history has unfolded. The distant future can now recede. You have followed the story from a cold cloud, through a hidden protostar, across a disk of dust and ice, into moving planets and the long calm of the present. You do not need to follow it any farther. The solar system does not require you to keep watch. The planets continue without effort from us. The moon continues. The earth turns. The old motions carry on beneath every sleeping room and every quiet sky. For this moment, the story has reached its resting place. Not an absolute ending. Not a final stillness. Only the present point in a very long journey. A middle-aged Sunday. A turning earth. A night that asks nothing more. The distances can soften now. The names can fade. The cloud, the disk, the planets, and the far future can drift beyond attention. There is only the steady world beneath you, the slow passage of the night, and the ancient solar system continuing its quiet motion, whether or not anyone is awake to notice.